All right, what I've done here on this handout that I just gave you, I've taken chapter 31 and tried to summarize it into some basic design criteria for beams. Like I mentioned, when we come into doing the structure for a building, columns and beams are really kind of how we transfer loads, right? We bring a load down, we hit a beam, we then take it sideways to a column, and we transfer it down eventually into the footing and the soil. So when you're doing beam design, chapter 31 goes into much more detail than this, but they look at different types. What I'm talking about here is something that I would recommend that you can do if you feel comfortable with it, but like a disclaimer, make sure you do, okay, before you do. If not, pay the money to have a professional look at it. Okay. There's my disclaimer right there. Okay. Now, what we're going to look at is only simply supported beams, which means that we have support on the end pieces only. Okay. When we start talking about complex, what we then have is we have beams that are supported from multiple locations. And the whole dynamic changes when that goes on. So again, if you're interested in stuff like that, that is taught here at CSI in the pre-engineering program. In statics and dynamics, they get you started at it. You really have to go to a university and take a class called Mechanics and Materials that would then line this out. Okay, you'll probably get that in a couple of years up there, once you get through your math high enough. So in essence, we're going to go through this. Now, the first two steps on here are wood, which we did in architectural. We're going to do it again tomorrow. What you're going to do with beams is you're going to figure pounds per linear foot. Okay? You're going to see that we actually design beams based on the sectional, cross-section area of it and the amount of deflection that that area will see. There's really no reason a beam should fail under normal operating conditions. Okay? Because we're going to put some fudge factors in this thing to help us out. So you figure the load, pounds per linear foot. Remember, if you know the dead load, you can add it all up. That's your dead load, then you apply your live load factor. Okay. For ours, we're going to use 20 for dead load, 60 for live load. Okay. From there, we go to a wood chart, pick it out, and run with it. Okay. When you're using a chart, make sure that it has the same dead load, live load calculations that you use. Okay, make sure of that. I will tell you from experience, we can get some really nice wood beams up to a little bit over 20 feet. And then they start getting so big that you have to start hunting for space. And you're going to have a lot of space for these things to work. Okay. So that's kind of the raw number. You know, you get over around that 20 feet area, and you're going to have to start making concessions. Okay. So we've got a couple spans over 20 feet. Okay, we want to look at those. If that doesn't work, then we go through the steel section. Now, let me explain what we're doing as far as the calculations go first, and then we'll go apply it. Okay. Again, this is just a standard setup. They go through this exact same process in chapter 31. Now, we do it by section, modulus, and deflection. Now, just to show you, it's all based on code. So this is kind of different, but I'm going to the last step first. Okay. Your answer from above must be greater than, and I can't remember what Greek letter that is, that's a deflection symbol, must be less than the length divided by 240. Okay. Now this is for different areas. Chapter 31 runs you through it. If you're doing ceilings, you can have more deflection, or roofs, excuse me, stuff that we never see. If you've got plaster on it, we use a little bit more. This is a general deflection note. So you can do this very quickly by coming in and saying, what is our deflection for our beam? It is equal to 35 feet, right? And we're going to look at just that main beam across the front. Divide it by 240. Okay. What do we get for a number? You're going to be doing a lot of calc in here, by the way. If you don't have a calculator out, you might want to grab it.
1.75, does that sound right?
It does. But forgot something in there on that calculation. This is feet. I know that there is 1 foot in 12 inches. Foot. Okay, try that.
I did that. I times 35 by 12 and then divided that number by 240.
Oh, yeah, that's not the right number. This is in feet. You should be somewhere around 1/4 inch on this.
So just do 35 divided by...
Yeah, this formula is in feet.
Okay.
Length in feet.
Yeah, 0.14.
Okay, so 0.14. This 240 has feet built into it. It's a standard, but it comes from a section modulus and modulus of elasticity. So make that correction in your notes. I didn't have that on there. That L is equal to length in feet. Okay. The 240 is a constant. Okay, so that 35-foot beam, what we're saying here is that it cannot deflect more than 0.14. So that's a little over an 1/8 inch, right? An 1/8 inch is 0.125. So what that means is we've got this beam coming across here, so we're going to have a column here and here. That beam will not be able to deflect where that distance is greater than 0.14. Okay. Now, with that, why do we do deflection? Well, one, we don't want the beam to fail. Okay, but the deflection is really there, not that the beam's going to fail. You're going to kind of see through our calculations when I run that there's almost no way under normal conditions that this thing would fail. But we do get unnormal conditions. That's where they do fail. But the core to that 1/8 inch that we want it to deflect, that's going to keep the drywall from snapping and breaking underneath, pulling wires apart, plumbing, whatever goes through those areas. Okay, so we just don't want to minimize all of that havoc that can come from something moving too much. Okay. Now, let me come back up to the top. So we're on step 3 here. When you do steel beams, you're going to do it off of deflection, but you got to do a little bit to get there. First thing you got to do is you got to figure your moment. Okay. So the moment is how much that thing will deflect per a proportion amount of load. Okay. So we're going to solve for moment. Now we've got a couple terms on here. You got W and L. W, uniform load on beam, pounds per linear foot. So we only need to analyze 1 foot of that beam. This is not for point loads, by the way. This is for continuous loads like a concrete floor, that kind of stuff. Okay, it's not a point load like a big air conditioning unit sitting in one spot. L is the beam span in feet. A is the constant. Once we get the moment, we're going to come down and we're going to estimate the section modulus. Now, the section modulus is in essence a factor that tells you how much steel you have in your shape. So it's really kind of a volume term of this shape, okay, is what it is. That's what we call a section modulus, or how much steel you have. Because we do steel mostly by volume. So that's what you're doing here. So you're taking the moment, you got a conversion factor to take it out of feet and get it to inches, and you're dividing it by the bending fiber stress of steel. Okay, now here's where a huge fudge factor comes in for structural, and why beams will probably never fail under normal conditions. Notice F sub B. You had to look this up. as one of your questions for review, you were looking at glue lambs versus Doug fir, right? And you saw the difference in the two? Well, F sub B, the bending stress of steel, is going to be 36 or 60,000 PSI. Okay, in this case, for mild structural steel, we're going to use 36,000. Now, we have to take, as part of code, you have to take your bending fiber stress and times it by 0.67. Or you're only going to be allowed to use 2/3 of the strength of that beam. It's a fudge factor. We're taking 1/3 of the strength of the beam and throwing it away and saying, we're going to design it that's extra. You know what I kind of see by that?
That's the F sub B.
Yep, right here. Okay, so we take it, if I times it by greater than 1, I would be expanding the strength. I'm just timesing it by less than 1, I'm reducing that strength. Can't use the whole strength of the beam. And the 2/3 is a constant. We use it with wood, we use it with strong, 60,000 PSI stuff, whatever we do. You always times the bending fiber stress by 2/3. That's why I make that statement. A beam should never fail under normal conditions, because we're saving 1/3 of the strength. Once we get the section modulus, you're going to go to a beam chart and you're going to look for them. So go to beam chart using S, check for deflection, and you're going to see a column on all these different beams where they've calculated the section modulus of these different shapes for you. So you're going to pick one, and then you're going to run it through a deflection calculation. Now this is based on the section modulus of the steel. So you got 5 times the weight divided by 12, where the 12 is a conversion factor. You got your length times 12, that again is a conversion factor. Notice that term is to the 4th power. Okay, so we've got to be careful there. That's the 4th power, and the reason we have to do that one is because of I. I is to the 4th power, the moment of inertia. Then you have a couple, this is the modulus of elasticity, this is the constant. Okay. So we've got a lot of big terms and big numbers here that we're going to have to deal with. Now, once you get an answer here for this deflection, it has to be less than that. If it isn't, go pick a bigger beam. Okay, that's why I say on here, this is an iterative process. Okay, we're going to pick one, we're going to run it. Does it work? No, it doesn't. Go pick another one, run it. Does it work? Yes, it does. That's the one we use. Okay? Now, following this chart, I copied a W-beam catalog for you. Okay. Now, as you come through those, let's just kind of real quickly look at the chart so you know what you're looking at. Okay, so first on the top here, see if I can get this whole thing. You have all the dimensional information right here that matches up with all your stuff you've got down here. Like K1 is right there, K is that one. It's all given to you. By the way, if you need to draw this end view, you can get all the information right here. There's another way to do it. You just went through a class on it?
String.
Huh?
Did you say string?
No.
No.
Oh, is that the STL thing that we put in our?
Type STL after you loaded your Autolist program and choose the beam you want. It'll draw it for you. Okay. Depending on which way you're looking at it, even if you want a 3D model of it, don't forget that. It's going to come in handy. All right, now as you're coming across here, notice there's some other things. So you're talking web, flange. Okay. So there's all of that information. Now it goes on to the next page though. So there's all that information, which is your dimensional information. Now if you come over right across from it, you'll notice, I got that still on the page. Okay, so here's still the other thing. This is a 8 by 67 we're looking at. over here, when you look at the axes, what we're looking at is the XX and the YY axes. So there's I and S, the section modulus, for both of those. And you can kind of see from the above figure right here, the X section modulus is taken in that location. So it's the web area. The Y one is taken lengthwise through the center. That's for a rotational item. We're only going to look at it in the X direction. If we had a torque or a rotating type of force, the X one is going to handle up and down, right? Because I'm looking perpendicular to that. The Y one looking this way is for a rotational force, torque. Okay. We don't need to look at that in this situation because we're going to have a rigid structure and all our weight's going down. Nothing's coming from the side. Okay. If I was tapping, by the way, if I had another beam toped in right here, would I now have a sideways force?
Yes.
Yeah, this is going to have weight on it, right? And that thing's going to pull. Then I would have to look at both axes. We're not going to get that into that situation. And in fact, we're getting into areas that even with my background, I wouldn't touch it. Because I haven't really done that type of work. Okay, and it's very specialized. All right, so there's all of our information that we need. All right, let's pull out our pencil and calculator and let's get a little bit of information. You might want your plan view. The beam that's obviously going to be metal is this front one right here. Okay. Now this is the situation we're going to look at. First thing we want to know, what is my moment force on this beam? By the way, 35 feet, you aren't going to find a wood chart that gives you a wood beam at 35 feet. You might find some glulam ones, but that's certainly not anything else. So, first thing we need to do, there's our situation, we're 35 feet, right? We know that half of this is being carried by the building back here. So we're only 5 feet, right? Halfway again. So we can now figure the moment force. What is our W equal to? It's the weight on the beam in linear feet. So W is equal to 5 foot times 1 foot.
145.
No, let's see. We're going to use dead load, live load. Times dead load plus live load. So, Sean, you were going straight to the concrete weight.
Oh, yeah.
We could add all of that up, but we're going to lump it into the dead load. Okay. So remember, we're using this as 20 and this is 60. Okay. So W is equal to what? Am I right? 400? 5 times 8,
40.
40. How did I get 35? 8 times 7? Okay, 400. That's pounds per foot. So therefore, M is equal to 400 times my length squared, and that squared is divided by 8. We're gonna need this number again.
Is it a big number?
It's gonna be a very big number.
61,250.
Can I get somebody to confirm that?
Yes, that's right.
Okay. Yeah, because we're taking 435 squared, it's gotta be a pretty big number by itself. Okay? So we now know the moment.
If it's good for you, then I'm fine.
Are you guys okay, or we good?
Yeah, I was just making sure to the board.
Is the moment unit, pounds feet?
It's actually gonna be foot squared, one's gonna cancel, it's pound feet. I've left all the units off of this because it's standard, and if you track the units, when you start going to the fourth power, it gets to be a headache.
And where do you get the 8?
The 8 is a constant.
Oh,
It's a constant. These are formula built off of the properties of the material. We'd have to go calculus to see where all this stuff's derived from,
oh.
and we're not going there. These are set equations. We're getting the end result of somebody sitting down and working all this out. Kind of like when we did trig, and I said, yeah, here's Pythagorean theorem. I'm not going to go over how it was developed, but it works. Same comment right here. Again, if you want to know how that works, you need to know an engineering program. Not architectural. Architectural does not go into this stuff. All right, from there, we now know the material, what we have to do here to get our section modulus. Okay, so this is going to be equal to, S is equal to 61,250. Okay. That's going to be times 12, that's a conversion factor, over 0.66 times 36,000. We're going to need, now we won't need FCB again.
Wait, what is the S for? Isn't that the deflection?
No, S is a section modulus. So it's the volume of material we have. It's this one, kind of a cross-sectional area. How much steel do we have?
And the 12 is put in the inches.
Yes. Yeah, because F sub E is in inches, right? Counts per square inch.
4.0.
Okay, so our section modulus is 4. Can I, again, I want somebody to confirm that number, please. What'd you get, Missy?
Not the right answer. Does it say
Maybe
4.0?
you did.
I was getting,
I'm
getting
getting
like
30.9.
I
Yeah,
got,
I was
I did
thinking
it
about
again and I
40.
got 30.9 as well.
I was like recalculating because I was like, did I get it wrong?
I know.
No, I did it again and I got 30.9.
Yeah, 31.
Yeah, these are big numbers. It's real easy to get a typo. That's why I always ask for a confirmation. So 30.9. I'll wait just a moment while everybody punches that and make sure you can get it. Kind of thought that 4 would be a little piece of plate. This is in essence an area term. One, did you get it?
Yeah.
Okay, so S is equal to 30.9. Now, what we then do is we just use that as a guide to go pick a shape. In my experience, this is generally going to be too small. Okay, generally. So, but it's a good place to start, because if you go to that catalog, we got a whole lot of them to choose from. This will give you a good starting point. So what we're going to now do is go to our catalog. And all you're paying attention to here is under the axis X by X column. You have capital S underneath there. You just run down that chart and we find one that is approximately equal to our 30.9. And you kind of see that there's one right off the bat, like it looks like the 8 by 35 is real close to what we got. Now you're going to get a lot of choices here. We're starting with the section modulus. I have a feeling the wood beams we are going to use are going to be 11 7/8.